Thank you very much for inviting me. I remember when we were preparing for O-level exams, way back in prehistoric times, we had to study geography, and also geography of South Africa. So we learn about the major cities, the rivers, the currents, and so on. And one city was Witwatersrand, or the name I had heard, Witwatersrand. It was very exotic kind of name. So I'm glad to be here at this university and see for myself what I would read about when I was a child of 15 years old. So this subject is has to do with the electron. It's a simple elementary particle. Every chemical reaction, you charge your cell phone, you run your car, electricity, electrons flow, and you don't pay any attention to what's so special about the electron. What you find is that the electron is negatively charged, and so here's an imagined picture of an electron, and it has a volume. So we learned that like charges repel, so the repulsion within the electron trying to expand its size, but it is stable. This is the heart of the question. Why is the electron stable when with everything that we know it should expand, it should in fact explode, releasing a lot of energy? So this is a little history of the electron since its discovery about 120 some years ago. And there are several attempts to find the reason why the electron is stable. So you can see here that it should really explode, releasing infinite energy. And yet it doesn't. So the electron knows something that we don't know about. It's able to keep itself stable when all that we know tells us that it should simply explode. So what might be the outward pressure? Estimate what that might be to say, okay, here's the energy electron in E squared over R. It's put it here for dimension. And divide by some volume. Volume means radius. What might be a guess for its radius? You can choose the Compton wavelength. You can choose the classical radius. Nobody knows what this radius is, but before you leave this room today, you will know what the radius is. So now you can guess, let's say it's the Compton wavelength. You put this number in there, and you find this is the energy density just due to the electrostatic repulsion within the electron. Look at this number. I mean, this is at about 13 atmospheres. The electron is a highly stressed particle. Just a simple calculation showing you this. Now, so these pressures, pressure means energy density, and energy density means that it affects the metric around it. The metric does not remain flat with such high energy density. You see that, for example, in the center of the sun, the outward pressure is less than this pressure flowing. In the sun, for example, there's outer pressure from the gas, but inward gravitational pressure keeps it stable until the hydrogen runs out and explodes. Now we know that energy density alters geometry, and geometry alters energy density. In Wheeler's statement, matter tells space-time how to curve. Space-time tells matter how to move. This is the Einstein equation. So here we have a case where the energy density is so high that you have to bring in the Einstein equation. Space-time is no longer flat. So you compelled to bring in relativity. So I've got this applet shows you what radiating charge does to the field surrounding it. So here's a oh, maybe some fellows. So here you are. You have a positive charge, and it has electric field lines radiating from it. And if you give it some acceleration, it will show you how the field responds. So we can see like this. How do I click over here? Sorry.
Sure.
All right. How do you watch over here?
Yeah, so whichever
okay.
is not presenting on
All
the screen.
right. Okay. So if you this is the demonstration of Larmor's formula. Just give it a sinusoidal charge is accelerating up and down. You see how the fields oscillate. And you can control the frequency, the velocity. But the interesting thing occurs when you stop. Now let's give it a bump. Watch carefully how the field responds. Okay. There's the radial part and then the variation part. The retardation sets in if the speed of light is constant. And when the field lines cannot follow, then they begin to oscillate and radiate. So if you go back. Let's go. If I capture one of these bumps. Look over here how the field has a radial, and over here is where the retardation sets in. You have transverse component and radial. So imagine a circle through these kinks, which is a sphere. Radial fields. What is the near zone? This is the radiation zone. Radiation zone, near zone. And this is something, look at the hydrogen atom. Okay? It's only 1 angstrom plus. It radiates, then the optical wavelength is 5,000 angstroms across. The radiation is happening over here. This is 1 angstrom, this is 5,000 angstroms. This near zone is huge. So the mechanism is that the charge pumps energy into this near zone. The radiation takes place at the surface of the near zone, not from the charge itself. Not from the charge itself. Okay? And when this thing is accelerating, it pumps energy in here and it reacts back with an extra inertia that the accelerating charge feels because it's putting energy into the near zone, which it falls back. So a charge, what is the mass of the charge? If you move it, it requires extra mass because it's mechanism. So near zone, radiation zone, and the accelerating charge. This is what you have to understand for the rest of the talk. So here's the retardation effect. And the near zone extends to when Kr equals 1. K is 2 pi over lambda. So the radius of the near zone is lambda over 2 pi. If lambda decreases, so does R. So as you move it faster and faster, the near zone shrinks down. Energy density goes up as fourth power and space-time curvature. Now, what is agitating the electron? So the vacuum field that continuously pushing the electron back and forth. That's what causes this radiation reaction, and the extra mass the electron acquires because of this. This is just in words what I just said. Now, since there is no lower limit on lambda, current theories predict that the mass will increase to infinity. It's called the problem of electric field, electron, that it should explode. The energy should explode. What makes it not explode? What stops this? Effect from going to infinity. That's what we're going to talk about. So if you've seen this before, the Feynman diagram, first order, here's the world line of the electron, it emits photon, reabsorbs. Emission and reabsorption means what? Why doesn't it radiate? Because it's happening in the near zone. It emits and reabsorbs in the near zone, the bound state. So, if you use this first order expansion and calculate the change in the mass of the electron, you get this integral. Okay, now let's look at it properly. This is the change in mass. U as a Dirac wave function, gamma as a Dirac. K is the photon momentum, P is the electron momentum. And if you look carefully, the mathematicians, there's a singularity over here which you can take care of, but integral is logarithmic. If k goes to infinity, the integral goes to infinity. There's no way to avoid it. No way around. So this was known since 1945. Now, mathematicians since Babylonian times, 5,000 years ago, cannot handle two entities, infinity and zero, because you cannot use multiplication, division, addition, subtraction. So we are trained to avoid infinities. Go around it, residue theorem, do a series expansion, asymptotic series, whatever it is, try to avoid infinity. So since 1945, people have said, okay, how do we stop this integral? Well, let's put a limit. Compton wavelength. We just say k will not go beyond the Compton wavelength. Stop it there. Or you can alter the laws of Coulomb's law and so on by saying that very short distances, Coulomb's law doesn't quite work. So, there are the leading terms, but still the lost term remains. No way out. Another attempt was this to say that space-time dimensions are not just four, they're continuous. 0, 0.1, 0.2, 0.3, 0.4, 0.5. And we do all the calculations with this continuum distribution of space-time dimension, then we'll say this 4. That makes it even worse. So they all attempts to get around infinity, but it doesn't work. If you know these people from physics, these are giants of 20th century. Okay. So I've got this quotation for you guys. You need an approach not from a mathematician point of view, but from a physics point of view. Nature is telling you something. Infinity is not something, artifice that's come out of your calculation, it is real. If you deal with it, find a way to interpret it. So go back to the near zone, right? If the energy is high enough, space-time is on the flat, and you have to bring gravitation. Nature is telling you have to bring in gravitation. So I've got this picture here. I was trying to find a way to explain this to students, and I thought how to show this. Eventually, this is my solution. This is a photograph. I took a baking dish, a transparent baking dish, and I glued a glass paper below it so you can see the grid at the top. You put a small amount of water, about 5 millimeters deep, and put a sharp wire just dipping the surface. You can see how the geometry is distorted. It's a Schwarzschild solution. So picture this as the electron. Okay. Geometry of the electron is now altered because it's high energy density. So keep this picture in mind. Okay, so now you have to use Einstein equation. We just need two of these components. We just say the near zone is spherical symmetric, and it is viscosity. Perfect fluid, spherical symmetric. So we just need the density term and the pressure term. So what is density? What is the pressure? Take the electron, if you squeeze it like an orange, apply a pressure, how does the density change? I need to know that. How stiff or soft is the electron? So we can use this equation, say, the first law of thermodynamics. So dE is minus P times change in volume. So, and the energy is equal to the energy density times volume. So dE is this. So eliminate E between these two, and you get an equation that relates pressure and density. And the density is connected to the gradient of the mass that I showed you earlier. R. You put this into the volume part, right? This is delta M. So here is the equation I showed you earlier. But now we're going to use this to calculate the density. Density, you get the pressure. So now you have the equation to state how much would you squeeze the electron to change its density by how much. So now I'm going to carry out the integration, but not with an infinite upper limit, but with some finite limit, which is unknown. So okay, there's some finite limit for k. And I have a new variable, which is the Compton wavelength divided by the radial separation. So if you carry out the integration, you get this. You can see it's the log term. Rate of density again is the derivative. Now we do some algebra. To insert pressure, the density over here, eliminate these two to get one variable, and this is the equation now. The rate at which the pressure changes with the rate of displacement in terms of known quantity. And this is called, if you know astrophysics, it's called the Tolman-Oppenheimer-Volkoff equation for hydrostatic equilibrium of a star, like the sun or the neutron star or white dwarf and so on. And something else to notice is that the derivative is negative, so at some value of R, this pressure will go to zero. I want to know where did the pressure go to zero. It means at that value of R, the outward field pressure equals inward metric pressure. And that will define the radius. So the stability comes from its own gravitational field pressing down on itself and balancing the inward and outward pressure. So if you go through algebra, you find that this is the electron radius. And it is in terms of universal constants. And LP is called the Planck length. So this factor times the Planck length, and it comes out to be 10 power minus 37. It's very, very, very small. You can see the pressures on the surface are this much. This homely electron that we don't think about twice is a highly stressed object. The stability comes from this mechanism. That's what I'm saying. Again, this is all the exact solution, and no assumptions over here. Textbook physics. Standard QED, standard relativity, standard. No assumptions here. So these are the conditions under which the system is at equilibrium. Furthermore, it is a stable equilibrium. If you squeeze it more, it's going to bounce back. If you stretch it out, it's going to push back in. Stable equilibrium. Okay. So you call it auto-stabilized. It stabilizes itself. There's no external source needed to stabilize it, but it stabilizes itself. So now we just, the alpha is just this quantity. Now the corresponding energy is given by this expression in terms of Planck length. At 10 to the power 17 GeV, this is the energy where all the forces, the electromagnetic force, nuclear force, weak force, gravitation, merge into one. So the universe began at the Big Bang, only one force, one field, then condensed out into other fields at this time. Now, you can see here this H bar, and alpha also has H bar. So H bar will cancel H bar, and the result is only in terms of E, C. There's no H bar beyond this. Now, what might this mean? H bar, we learned, is a measure of quantization. Objects which are small enough, they don't follow classical physics. We have to treat them as quantized objects. There's no H bar telling you that the field is continuous. It's not quantized. Unified field is not quantized. It's something I find hard to believe, but this is what the equations are telling us. So here are the conclusions. So we found a way to stabilize the electron. We found the radius, and we also been able to calculate this what's called grand unified theory. Field, unified field, looks like it will be continuous, and is a successful theory of quantum fields in. Put this quotation up. Thank you.